Okay, so integration for quickly approximating sums. Integration for sums. Okay, so let me remind you what a sum is. Okay, a sum is, we introduce this notation, I equals 1 to, let's say, 5 of, f of I is f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5. Okay, and we generalize to even if the upper limit is n. So let me show you what this looks like on a picture. Okay, so let's draw, f of x. So here's 0, 1, 2, 3, 4, 5. Let's put in 6. Okay, and now I'm going to make an assumption. Let's assume that this function f is increasing. Okay, so it looks something like this. Okay, it's an increasing function. Now, let's consider what f of 1 is. Okay, so f of 1, okay, is this, summation here, is this value here, but that's exactly equal to, okay, the area under this block. So this here is f of 1. Okay, because the height is f of 1 and the width is 1. Okay, and similarly, this is f of 2. This is f of 2. And it's equal to the area under this block. Okay, and then f of 3 is the area under this block. And f of 4 is the area under this block. And f of 5 is the area under this block. Okay, and now observe, okay, that the area under the curve, which is the integral from 1 to 6, so the integral from 1 to 6 dx of f of x is the area under the curve. Okay. And the area under the curve exceeds the area under the blocks by some positive amount. Okay. So that means that the area under the curve is at least the sum of these, areas of these blocks, which is the sum from I equals 1 to 5 of f of I. Now look what happens if instead I drew the rectangles, instead of to the right, I drew them to the left. Okay, it's because this function is increasing, now this line goes above the curve. Okay, and so, if I drew the lines to the left, okay, if I drew the blocks to the left, I have a very similar picture, but this is now f of 1. This is now f of, this is f of 1, this is f of 2. Okay, so I'll write it on top. So this is f of 1, f of 2, f of 3, f of 4, f of 5. Okay. And now if we compare the areas of the blocks, okay, compared to the area under the curve from 0 to 5, we see that the area under the blocks overestimates that area under the curve from 0 to 5. What that means is that the sum of these 5 blocks, which is the sum from I equals 1 to 5 of f of I, is at least as large as the integral from 0 to 5 of dx f of x. And so here, by integration, providing that f is monotonically increasing or non-decreasing, we have rigorous upper and lower bounds. Essentially what we're saying is that, f of x is approximately equal to the integral from, 0 to 5 dx f of x, or 1 to 6 dx f of x, or maybe half to 5.5. But basically we can approximate the sums. We can approximate the sums by integrals. Sum from I equals 1 to 5 f of I is approximately equal to the integral from 1 to 5 or 6 of f of x dx. This is strictly speaking an upper bound, but most of the time this upper bound is accurate enough to give you a theta analysis. So it gives you the right order of magnitude, the right growth rate. So let me summarize this discussion in a more general theorem. If f of x is non-decreasing, okay, that means basically increasing, okay, then the sum from I equals m to n, so we don't have to sum from 1 to 5, we can go from m to n of f of I, is at most the integral from m to n plus 1 dx f of x, and it's at least the integral from I equals m minus 1 to n dx f of x. And this is a special example of that. This can be derived analogously. Oh, what happens if f is instead of being non-decreasing, it's non-increasing. So f was decreasing, then you just flip these signs. The inequalities are flipped, are reversed, if f is decreasing. Okay, or non-increasing, to be more specific. Okay, so integration gives us a nice way to bound sums. Let's do lots of examples. Okay, so examples. Okay, 1. The sum from I equals 1 to n of I to the k. So we did the sum of the integers, we did the sum of the squares, we did the sum of the cubes, and it's getting hairier and hairier. But if we approximate this by an integral, this is approximately equal to the integral from 0 to n dx. So f of x is x to the k. So this is I to the k. So this is f of I, where f of x is x to the k. So dx of x to the k. Well, that's just equal to n to the k plus 1 over n. So it's this is an approximation. Technically, this is a lower bound. We could get the upper bound by integrating from 1 to n plus 1. Okay, and this is equal to n to the k plus 1 over k plus 1, and this is in theta of n to the k plus 1. We ignore the constant k plus 1. So we immediately got the growth rate of a summation that involves the powers of the integers raised to some power k. Let's do another example. 2. Okay. The factorial. So log of n factorial. Okay, now this is a bit trickier. I have to first put it as a sum. This is the sum from I equals 1 to n of log I. So because log of n factorial is log 1 plus log 2 plus log 3 up to log n. Because the log of a product is the sum of the logs. But now I can set f of x equals to log x. Okay, and so this is approximately equal to the integral, the integral from 1 to n plus 1. So technically, this is strictly speaking an upper bound, but I'm just saying approximately equal to the integral from 1 to n plus 1 dx log x. And for calculus, we know how to do this integral. This is exactly, x log x minus x evaluated at the endpoints n plus 1 and 1. So n plus 1 and 1. Okay, so this is equal to n plus 1 log n plus 1 log n plus 1 minus of n plus 1, okay, plus 1. So n plus 1 log n plus 1 minus n plus 1, okay, and then minus the evaluation at 1, but log of 1 is 0, and so you get a minus of minus 1, so plus 1. So these ones cancel. So this is equal to n plus 1 log n plus 1 minus n. Okay, but the highest order term is the n plus 1 log n plus 1. And if you work this out, this is in theta of n log n. That's very nice. So if you have algorithms whose running time is logarithm of n factorial, then that's essentially in the set of functions which are n log n. Let's do another example. The harmonic numbers. 3. Harmonic sum. So what's the harmonic sum? Hn is equal to 1 plus 1 over 2 plus 1 over 3 plus 1 over n. So here, this is equal to the sum from I equals 1 to n of f of 1 over n, 1 over I. So f of x is equal to 1 over x. Okay. Now, this is not an increasing function, so we cannot apply the theorem. Okay, it's not a non-decreasing, but it's a decreasing function, so we can apply the theorem with the inequalities reversed if you want strict bound. But approximately, this is approximately the integral from 1 to n, let's say, of dx log x, dx 1 over x. Strictly speaking, to get an upper bound, I should integrate to get a lower bound, I should integrate up to n plus 1. Okay, this would be a lower bound, and if I integrate from 0 to n, I get an upper bound. Okay, but I can't integrate from 0 to n, so I'm going to get the lower bound and say that this is approximately, we can, this is equal to the log of n plus 1. So technically, what I've proved is that Hn is at least as large as the log of n plus 1. You can use the integration method to show that it is at most 1 plus the log of n. Okay? And So that's nice. So if you're analyzing anything and the amount of work you do or the quantity you're analyzing is 1 plus a half plus a third, it's gradually decreasing. Okay, so that's what we call the harmonic sum. The full sum is growing logarithmically in n. Okay, but it's growing logarithmically in n. So this sum, even though the term is going to 0, this sum is actually infinite. Okay, when you take n goes to infinity. Okay, one last example and then let's quit. Okay. So this integration method is just a gem. It allows us to approximate sums very quickly. So let's do a recurrence. Okay. So let's do a recurrence. And I'll take the one that's done in the book. So let's suppose that you have an algorithm whose running time on an input of size 1 is 1, and the running time on n is equal to the running time on n minus 1, so it's a recursive function, plus you do an extra amount of work, n root n minus log n. So just to show you how we analyze recursions, let's unfold this recurrence. So we have t of n equals t of n minus 1 plus n root n minus log n. T of n minus 1 equals t of n minus 2 plus n minus 1 root n minus 1 minus log n minus 1. T of n minus 2 equals t of n minus 3 plus n minus 2 root of n minus 2 minus log of n minus 2. Okay, and so on. Ultimately, we get down to t2 equals t1 plus 2 root 2 minus log of 2, and then t1 is equal to 1. Okay. So we've unfolded the recurrence. There's this dot, 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 but we're not proving a formula. We're just trying to analyze. We're trying to unfold. Okay. Now, if you add the left and you add the right, you will see that this term cancels with that. This term cancels with that. This term will cancel with a term below, and so you get a lot of cancellations. And what you end up with is tn minus 1. This tn minus 1 cancels with tn minus 1 here. So what you end up with is tn is equal to n root n minus log n. N root n minus log n. Plus n minus 1 root n minus 1. Root n minus 1 minus log n minus 1. Plus n minus 2 root n minus 2. Minus log n minus 2. Plus all the way down to 2 root 2 plus 2 root 2 minus log 2. And then plus 1. Okay, so 2 root plus 1. Okay, and we could, if we wanted to, we could subtract minus log 1 just because log of 1 is 0. And when you add all of this up, you get the sum. You get the sum from I equals 1 to n of I root I. Okay, minus the sum of log 1 plus log 2 plus log 3 up to a log n minus, so the log of 1 plus log of 2 plus log of n. Okay. Well, we analyze this sum. This is the sum of I to the k, where k is 3 halves. So this guy here is in theta of n to the 5, this is 3 halves, n to the 5 halves. Okay. And this guy here is log of n factorial, so we know that this guy here is in theta of n log n. Okay. So this thing is, n to the 5 halves. This is n to the 5, n to the theta of n log n. This is the dominant term, so the whole thing is in theta of n to the 5 halves. So the asymptotic analysis of this recurrence results in a running time which is n to the 5 halves. That's the growth rate of this running time. So if your running time has this recurrence, which would be a very unusual algorithm, you can quickly compute its running time. Okay. So what did we do today? We talked about sums. Why are sums important? They appear in algorithm analysis. So we need to be able to compute sums at times, but more often than not, we need to be able to approximate sums very quickly. In particular, in the asymptotic regime, ignoring constants of addition and constants of multiplication. Okay, so that led us to ways to compare functions, i.e. the growth rates, i.e. the asymptotic analysis, big-Theta. Okay, so we define, for example, the set of linear functions, the set of quadratic functions. Okay? It doesn't mean that your function is exactly quadratic, but its asymptotic behavior, its essence is quadratic. Okay? And then once we realize that we need to only compare functions in this asymptotic regime where we only need growth rates, it means we need quick ways to approximate the running time, to approximate sums. And one very powerful gem in that bush is the integration method. Okay, see you next time.